line. If the relation is increasing, the larger the base, the steeper the line or relation. Okay, time for practice. Some easy basic practice. It's not even 4 options, it's just 2 options at this point. Increasing or decreasing, what do you guys think? I'm going to get that poll up. Here's the results. A and B. So most people said B, some people said A. What's the answer? The answer is B. This is a decreasing function because my base value is less than 1. So remember, if it's a fraction, basically less than 1, or a decimal, then it is decreasing. Ooh, what about this one? Let's try this one now, shall we? Go for it. So this is what most of you said. Most of you said A. And the correct answer is A, yes, because 1.5 is bigger than 1, so it's an increasing function. What about 5.0? Try again. Okay. We have a 50-50 split here between A and B. The answer is this one is an increasing function. Why? Even though it's written as a decimal, you have to understand that it's bigger than 1. Obviously, if the decimal is bigger than 1, it's going to be an increasing function. The answer is A, increasing function. Let's do this one. So for this one, we have some people saying A, some people saying B. The answer is B. This is a decreasing function. Decreasing function. Because remember, this 0.5 is less than 1. That's all you really have to know. If the number is between 0 and 1, a fraction or a decimal, 0 and between 0 and 1, it's decreasing. So this one is decreasing. And if the number is bigger than 1, it's increasing. What about this one? Let's try this one. Okay. Here we have, once again, A and B. Most people got A. Most people got it right. Yes, the answer here is increasing. Good job. And I think this is the last one. Go ahead and let's try doing this one now. So here we have, majority got this one. B, decreasing is right. So good job. All right, practice, which is the steepest? This one is going to be hard. So how about I remind you the rule for steepness? Listen carefully. If a relation is increasing, the larger the base, the steeper the relation. If the relation is decreasing, the smaller the base, the steeper the relation or line. So let's do this now. All right, so here we have A, B, and C. No one picked D though. That's good. But let's see, what's the answer? Well, this is an increasing function. How do I know? Well, the base number is bigger than 1, so it's definitely increasing. And the steepest one is going to be the biggest number. So what's the biggest number? There's 3, 3.3, 3.03, and 3.0. So 3.3 is the biggest, and the answer is B. B is the biggest number here. Now we have another option. Let's try this one. Okay, well, here are the results here. A, B, C, and D. Most of you said C. Let's see if that's right. So this is a decreasing function. How do I know? Well, the number is less than 1. So we're looking for the smallest number here now. So 0.6, 0.66. Well, 0.66 is bigger than 0.6. 0.60. Well, 0.66 is still bigger. And 0.06. So 0.66 is the biggest. But are we looking for the biggest? The answer is no, we're not. When we're decreasing, we're looking for the smallest number. So the answer is C, 0.06. The answer is C. Congratulations for those of you who got it. For those of you who didn't, you got to do a little bit more practice. Now we're moving on to identifying exponential relations, linear, quadratic, or exponential. What's going on here? How do we figure this out? Same way we did it last time. What do I mean by that? We do the differences. First differences. I just realized I have to make 2 columns anyways, so might as well extend them. Okay. So you have your table of values, and you make 2 more tables right next to each other. For first differences, you usually block out the first block there, and for second differences, you block out the first 2 blocks there. How do we do this? You take the number on the bottom, 1, subtract the number from the top. So 1 minus 0.25, which is 0.75. Okay. Then you do 4 minus 1, which is 3. 16 minus 4, which is 12, and then 64 minus 16. Oh man, that's getting very hard to read. But here, 64 minus 16 was it 48? I think. Maybe wrong. Let me see. 54 minus 6. Yeah, that's 48. Here we have 3 minus 0.75, which is 2.25. Here we have 12 minus 3, which is 9. And then 48 minus 12, which is 36. So it's not linear, because if it was linear, then all these numbers, the first differences, would be the exact same number. It's not quadratic, because then the second differences would be all the same number. They're all different. So what's left? It could be exponential, or it could be neither. That is also an option that wasn't written here. So we still have to figure out whether it's exponential or none of them. Because it's very possible to have a function that's not linear, that's not quadratic, that's not exponential. It's actually more likely because, yeah. Anyways, exponential. How do we figure out exponential? Easy. Instead of subtracting the values, what you do is you take the values, your y values here, and you divide. So let's see what we get now. What's 1 divided by 0.25? That's 4. What's 4 divided by 1? That's 4. What's 16 divided by 4? It's 4. What's 64 divided by 16? It's 4. That is how you figure out whether a function is exponential or not. It's by, there's a few ways. Obviously, you can look at the equation if you don't have the equation, but if you're given a table of values, this is how you do it with a table of values. Instead of first differences, you're kind of looking for a ratio or a number that these y values are increasing by. So in this case, it's times 4 times 4 times 4 times 4. So 0.25 times 4, you get 1. 1 times 4, you get 4. 4 times 4, you get 16. 16 times 4, you get 64. So it's going up by 4s. That's it. That's how you do it. Growth and decay. We've got some growth models. To create a growth model, we use the formula. So final value is equal to initial value times the growth factor to the exponent, or to the power of the number of periods. This is confusing. We're going to do some examples, don't worry. To determine the growth factor, look for keywords. This is important. This is referring to word problems. So you're going to have doubled, which is 2, tripled, which is 3. Sometimes the growth rate is given as a percentage. When that occurs, we convert the percentage to a decimal and add a 1 to it. So what does that mean? Well, let's say the growth rate is 25%. Something's growing by 25%. So the way to figure out the actual growth factor, you take 25%, convert it into a decimal by dividing it by 100, so you have 0.25. Then you add 1 to it, and you get 1.25. So this is the growth factor, 1.25, when they say an increase of 25%. So let's do an example here. Oops. The number of ants in a colony doubles every month. There are 24,000 ants now. How many ants will there be in 5 months from now? Pretty straightforward. Let's go back to our general formula here. Here we have our formula. So our final value is how many ants will be there in 5 months from now. That's what we're looking for, right? Final value. Our initial value, what's our initial value? There are 24,000 ants now. So that's our initial value. So this is going to be 24,000 times, what's my growth factor? Well, the keyword is doubles. And if you remember, doubles means 2. Growth factor is 2. Oh, hey, Marlena. But yeah, 24,000 times 2. And then the number of periods. What's the number of periods? Periods means time. How many times is it, when does this double? It doubles every month. And how many months are there? 5 months. So the number of periods is 5. So this is going to be 2 to the power of 5. So 24,000 times 2 to the power of 5. At this point, you need to get your calculator out. Do 2 to the power of 5 first. Remember, BEDMAS, you have to do exponents before you do multiplication. This is going to be 24,000 times 2 to the power of 5, which, if you use your calculator, or do 2 times 2 times 2 times 2, sure you'll figure it out. It is 32. And then you do 32 times 24,000. The answer is 768,000. That's the answer. So that means in 5 months, right now there's 24,000 ants, and in 5 months there's going to be 768,000 ants. So this is considered a growth equation. It's growing. The population of ants is growing. Pretty straightforward, I think. What about a decay model? Decay model is very similar to a growth model. You still have the final value equals initial value times, but instead of a growth factor, you have a decay factor. And then to the power of number of periods. So what does that mean? The decay rate is given as a percentage. When that occurs, we convert the percentage to a decimal and subtract it from 1. This is key. A lot of students make a mistake here. They just convert it into a decimal and they don't subtract it from 1. This is important. So here we have an example. Ryan's new moped is expected to lose about 17% of its value every year. If it is worth $1,400 when new, how much will it be worth when it is 6 years old? It's a very real world problem. Cars or vehicles depreciate. Even just shiny new items always depreciate. after you buy